Okay, so Eg20. Find an expression for the gradient function for the volume of Descartes and hence find the coordinates of the stationary points. So we need to differentiate this for the gradient function, and we can see that we're not going to be able to rearrange that to get y equals, so we need to differentiate implicitly. So that means that we have to do d dx of x cubed plus d dy of y cubed equals that's d dx. We're differentiating the whole thing with respect to x. So I call that the original equation, equation 1, and this equation, equation 2. Now, because this is a multiple there, a product, probably going to be easier to separate these out and then come back and substitute them into that. So the first one is straightforward, d dx of x cubed is 3x squared, so that one's straightforward. d dx of y cubed is going to be 3y squared dy dx, so that's the implicit bit. Differentiate with respect to y and multiply by dy dx, and then we got the nasty twist at the end where we've got 3xy. So this is a product rule, so if we haven't learnt or if we're not confident taking a shortcut on this, let's do this the long way. So we'll let u equal 3x, we'll let v equal y. du dx will be 3, and dv dx, remember, we're differentiating implicitly, will be 1, we get if we differentiate that with respect to y, multiplied by dy dx. So when we differentiate 3xy using the product rule, it's going to be v du dx plus u dv dx. Okay, so we've got this one covered, we've got that one covered, we've got that one covered. So if we now substitute those into equation 2, so instead of d dx x cubed, I can write 3x squared plus 3y squared dy dx equals this, which we've done down here, 3y plus 3x dy dx. You can see that the 3's are going to cancel, so I can divide it throughout by 3. I want to gather my dy dx's on one side, so if I've got y squared dy dx minus x dy dx, that will equal y minus, bringing that over, x squared. Take the dy dx out as a common factor, and divide. Job done. So back to the question. Find an expression for the gradient function. Done. Hence find the coordinates of the stationary points. Okay, so for stat points, that equals 0. So y minus x squared over y squared minus x equals 0. When I take the y squared minus x over, it becomes 0, so I get y minus x squared equals 0. Y equals x squared. So I've now got an expression for y in terms of x. What I now want to do is to plonk that into equation 1 to eliminate one of the variables. So just create myself a bit more room here. So in 1 I'm going to have x cubed, and then instead of y I can write x squared cubed equals 3x, and instead of y I can write x squared. So I have x cubed plus x to the 6 equals 3x cubed. X to the 6 minus 2x cubed equals 0. So I can take out x cubed, leaving me x cubed minus 2 equals 0. Therefore, either x cubed equals 0, which will give us an x coordinate of 0, and then to work out the corresponding y coordinate, put that in 3, y equals 0 squared, therefore stat at 0, 0, or x cubed minus 2 equals 0, x equals cube root, and when we put that into 3 we get y equals 2 to the 3rd squared, which is 2 over 3, which is 4 to the 3rd. So the stat point is at 2 to the 3rd, or the cube root of 2, comma, cube root of 4. So that gives us the stationary points. Okay, so that's quite a detailed question, certainly up to an A-level paper standard question. Differentiating implicitly with an embedded product rule implicit, and then a little bit of stationary point work at the end.